not here, but I still wanted to go over the midterm a little bit because some of those questions were important. So let's start off with the first one. So I'm writing down. So to solve this one, I'm just going to do the half reactions and look at those. We're not going to worry about like writing out the whole thing and balancing it just because it's not important to the question. So we have H2 on this side, it's in its ionic form, and we have 2. This side, it's in its ionic form, right? So for hydrogen in its elemental neutral form to yield hydrogen plus, it will need to lose electrons on the reactant side. We can't write that. We have to write it like this. But this is essentially oxidation, okay? For fluoride, we have to gain 2 electrons on this side for it to yield its ionic form. And this is reduction, okay? So if fluoride is being reduced, then what is causing it to be reduced? The hydrogen. The hydrogen is causing the fluoride to be reduced. So the hydrogen is the reduction agent, okay? Since hydrogen is causing fluoride to be reduced, it is a reduction agent. And that leaves fluoride causes hydrogen to oxidize, so it is the oxidation agent. I saw some people got that a little bit messed up. It's easy to get it messed up, so don't worry, just practice a little bit more. Right, that's question 1. The next question was, what are some possible electrode metals we could use? The answer was all of them. You know, if you selected some of them, you got points, but the answer was all of them work. It's just that platinum, gold, and silver, yeah, they're kind of expensive, but they're still possible. So, all right, our next question is about the Nernst equation. And this equation is very, very, very important because it's only going to be asked during like states or nationals on the written portion, but we need this like fundamentally to do our build and understand what is going on. So our first question was, what is E naught? Okay, that's what that stands for. E naught. E naught, the answer was standard reduction potential, okay? Standard reduction potential. And as the name suggests, it's basically like how badly a chemical species wants to be reduced. So its tendency to be reduced. So if something has like a really high reduction potential, it really wants to be reduced. So let's look at a reduction potential chart. Now this one is you can see the pixels, but it's okay. You get the idea. You can search one up. It's like any standard reduction potential chart, right? This is our standard reduction potential chart. And reduction potential is measured in volts, okay? It's measured in volts, and we can see that right here. If we look for chloride, which, you know, part of our sodium chloride solution that they're going to give us, we see that chloride has a really, really, really high reduction potential. It's 1.36. It's pretty up there on the list. And we need to flip it for our purposes. So right now it's Cl2 plus minus 2Cl minus, but we want this to be oxidized. So it's going to look like that. Right? And when we flip it, that means our reduction potential is going to become negative. Negative 1.36. And for something to oxidize this, we need it to have a reduction potential that is bigger than 1.36 because we don't want it to be negative, which is a problem. It's really difficult to find things that will oxidize chlorine. But coming back, that's what that question was. It was, what is E naught? E naught is standard reduction potential in voltage. And on the same vein, we're asking what is E, which is the product of your Nernst equation, and that is our output voltage, which is very important for our purposes because that is one of the things we are trying to find. We're trying to find the voltage difference when we switch out for different concentrations of sodium chloride. So obviously, if we're trying to find a difference in voltage, we need an output voltage from our redox reaction, right? So this Nernst equation will solve and give you the output voltage of your reaction. So what is Q? Q is the reaction quotient in the Nernst equation. It's like, it measures the relative amounts of products and reactants during a reaction at a particular time, right? So when we're doing our reaction, we'll say, okay, this is important right now, this is important right now, and it's just the products and the reactants, we put it in there. We put it in terms of molarity because we're looking at concentrations, because that's what this symbol means. So yeah. Now let's look at a redox question that was a little bit more challenging. So the first question was, what type of reaction is this? This is single replacement, okay? A, B, C, right? So it'll yield, all right, it's a single replacement. And as we recall saying, all single replacement reactions are redox reactions, okay? So our question is, what is being oxidized? What is being reduced? We want to look at this side versus this side, all right? So here, K is in its ionic form. Sorry, K is in its elemental form, my fault. K is in its elemental form. It is a neutral charge. Here, sodium and chloride are in a compound, so they're going to be balancing each other's charges out. So this is Na plus, Cl minus. Here, KCl, I don't say KCl, say potassium chloride, my fault. Potassium chloride, that's in it's in a compound, so it's going to be balancing charges out. Look at that. And sodium is in its elemental form, so it's no charge. All right. Don't worry. I didn't balance this equation out, so it's unbalanced. But again, we don't need that for our purposes, so I'm just not going to do it. We're being asked what is being oxidized and what is being reduced. Well, if we look at potassium, right? Potassium goes from its elemental to having a positive charge, right? Which means we are losing electrons, right? Essentially, this is what's happening. So potassium is being oxidized. And if we look at sodium, sodium is going from a positive charge to a neutral charge, which means we are gaining electrons, and it is being reduced. Now, chloride is, if you write out the net ionic equation of this, chloride is just a spectator ion, like it'll cancel out. You can see like it goes from negative to negative, so it's not really important to us. So we want to focus on these. Okay? And the next question was, what is our oxidizing agent? What is a reduction agent? Well, what is causing potassium to be oxidized? Sodium chloride, that's causing potassium to be oxidized. So that is your oxidation agent. And what is causing sodium chloride to be reduced? Potassium. Potassium is your reduction agent. Our next question was identify and label the parts of this LED. It seems kind of dumb, but LEDs are still a thing this year in detectors, so we have to make sure to keep that in mind. This was the answer. If you didn't have exactly this, that's fine, because it was technically like it was really hard to see what was going on. So if you generally had something that seemed like it could have fit, or seemed like, I'm like, okay, yeah, I can see why you said that or where you were coming from, then I gave you the points. Mainly, it was the anode and the cathode that you'd want to pay attention to. Anode is the positive side, and cathode is the negative side. Our next question was the properties of a parallel circuit, all right? So when we're talking about a parallel circuit, we're talking about when a circuit has its components in parallel. So, for example, those squiggly things are resistors. This is a series circuit. It goes 1, 2, 3. You're just going in series and going all the way back around. This this is a parallel circuit. You see your resistors, they're in parallel to each other, right? And that will have different properties than a series circuit. So your answers here were A, B, and D. They all have properties of a parallel circuit within them. And I think the most important question on this midterm was describe what our ORP probe and setup would look like, detail the different parts of the probe, and set up and detail the role. Okay, weird phrasing. But I wanted to go over that, all right? So we know that one of our solutions most definitely has to be sodium chloride, because that's what they're giving us. They're giving us some concentration and saying, find the concentration and tell me what the difference in voltage between the mystery concentrations that I give you is, right? And we previously brought up how hard it was to oxidize chlorine because of its super, super high reduction potential. So we needed to find something that would do that. All right, and let's take a quick look at our options, if you can even see that, right? We had gold, all right, gold in its aqueous form. That's like good luck trying to find that. We had permanganate, which was an option, okay, that's not undoable. Hydrogen peroxide, that was pretty doable, and that's actually the one that we chose. And we had iron, which, yeah, that was not happening either. There were some other really, really super weird ones, but hydrogen peroxide was our best bet for now. So we decided to go with hydrogen peroxide. All right. So if our other solution is hydrogen peroxide, oh my God, then these would be our two solutions. This hydrogen peroxide would stay constant. We'd want to switch it out every single time we do the reaction because hydrogen peroxide has tendency to decompose. We're going to have to acidify it, right? I'm not going to go into why we're going to have to acidify it, but we have to acidify it. So we're going to use nitric acid, I think it's called nitric acid, to do that. We previously tried hydrogen chloride, actually, HCl, but newsflash, when hydrogen chloride and hydrogen peroxide come together, they will form a gas, and you will lose a lot of your reaction. So that will give you a very, 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 very large percent error. So, fun fact. So let's say we have an electrode here, an electrode here. It doesn't really matter what they are. Let's say both of them are copper. I don't know. Okay, so it's going to be connected to the whole other part of this event, the circuitry, which is essentially the voltmeter we're building. It's going to give you the readings, the concentrations, the voltages that we need, right? And we have a salt bridge. Talked about why we needed those, right? And I'm pretty sure we were using that for our solution there. Now, if you throw all of this together, you will get a voltage. You will get an output voltage. All right, so this is essentially how we're setting up our redox reaction. And what we're going to have to do is set up a Nernst equation to start calculating for all of these values, right? What we've done right now so far with this whole setup is we've gotten an output voltage, which is great. That's a really great first step. And now we have to solve for accuracy. We have to say, okay, what are our concentrations that we want? What is our voltages looking like? The other problem is that our voltage might not be big enough, right? If we're given concentrations and we're getting the tiniest difference in between our concentrations, that's a problem. That is a problem because we're not getting that much of a voltage difference. So what is that telling us? So we need a way to amplify our voltage reading, right? And let's take Ohm's law, V equals IR, right? We're really not getting much current from this whole reaction, right? So we can amplify this reaction by putting in a resistor, which is another thing that we tried, by putting in a resistor here. Okay, I don't know, resistor. Put it in the circuit, right? The bigger the resistance you have, the bigger the voltage. It's proportional. So we're thinking some real big resistance to really amplify that voltage reading so we can get a good difference in between the concentrations that they give us. All right, that's another thing we needed to pay attention to. And that was our midterm. I hope it all went well for everyone. I may have forgotten to go over some stuff, so if you have any questions, ask Darren or ask me, email me, tell Darren to tell me, or whatever. and I will try my best to go and answer them. And thanks for your extra credit responses. They were very, very fun to read. Bye.